Welcome to the office. We want to take a look at the two different groups of order 4, and we're going to observe that they're not the same group by recognizing the subgroups of the two different groups. So let's take a look at our two groups of order 4. The first is Z4, so we should be familiar with this. This is addition modulo 4, so it has the elements 0, 1, 2, 3. And the other one that we're not familiar with is called the Klein 4 group. So my apologies, that's probably a little difficult to read. Klein 4-group. Okay, so we have these two different groups. Let's first remind ourselves of Z4 here. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2, 0 plus 3, 1 plus 0, 2 plus 0, 3 plus 0, right? The identity element under addition is 0. Let's see here, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, but we're working in modulo 4, so that would bring us back to 0. 2 plus 1 is 3, 2 plus 2 is 4, and 2 plus 3 is 5, right? So 5 is going to bring us back down to 1 at modulo 4. Right, 5 is 4 plus 1. All right, so 3 plus 1 is 4. 3 plus 2 is 5. Modulo 4 is 1, and 3 plus 3 is 6. Right, 6 is 4 plus 2, so that would bring us to 2 there. So we see our table for C4. Excellent. It's a group. Life is good. I don't think we verified that it's associative, but indeed it is. It is associative. We have an identity that's 0. We have inverses. Notice that I can get 0 in each row, essentially, each row in each column. So life is good. Now here, the Klein 4 group has a more generic representation. So just E, A, B, C. E, of course, is the identity, so we should be able to fill that out relatively easy. So E, A, B, C, E, A, B, C. So I think they're using multiplication here, though the book doesn't actually give a notation at all. So if we call it multiplication, E times E is E, A times E is A, B times E is B, C times E is C. Similarly, E times A is A, E times B is B, E times C is C, right? It's the identity. That should be pretty straightforward. Now, I know that I want something that's different than Z4, so I should expect it to look relatively different as I start to fill this in. So what have we got here? So what I would like is that any number, any element times itself gives us the identity. So I'm going to have E along the entire row here. Sorry, diagonal. That's not row. Row, column, diagonal. Okay. Now what I want is I'm going to fill this in as A times B is C, and A times C is B. Now, we're essentially forced into that because I can't have B in this column here because B is already in the column here. Similarly, I can't have C in this column here because C is already right there. So I'm forced into that. Okay. I can use that same sort of argument for these two entries here. I can't have, let's see here, similar argument. Where did I want to go with that? Yes, okay. So I can't have A in either of these two entries. I can't have B here, so that has to be C, and I can't have C here, so that has to be B. Fantastic. And that leaves us with A here and A here. Okay, so as soon as we have one that's got the identity along the main diagonal, then along the diagonal, then right, we're limited. We're forced into that particular group. So if I remember correctly, these are the only two groups of order 4. That might not be the case. Let me double check here. Oh, yep. Yeah, I think that's right. I think that's right. The one that I had in my mind that I was trying to think of, I am actually realizing now that's in order 5. So I think we're good here with just the two. So subgroups can be hard to identify, but what we want to do is we essentially want to observe that if I wanted to find a subgroup, it's got to have 0 over here. And as soon as I include 1, then I can say 1 plus 1 is 2, so I've got to include 2. If I have 2, 2 plus 1 is 3, and there we go, we have the whole thing. So I can't start off with containing 1. If it has 2 in it, I can say 2 plus 2 is 0, and 0 plus 2 is 2, 2 plus 0 is 0. So, hey, look, I get a subgroup of just the elements 0 and 2. As soon as I include 3, 3 plus 3 gives me 2. So as soon as I have 2, then 3 plus 2 gives me 1, and I have everything again. So in order to contain 3, I have to have everything. In order to contain 1, I have to have everything. And of course, I always want 0. So this is the only subgroup that exists for this particular group. That's it. However, here, what I can notice is that this square right here just has E and A. So I can quickly observe that E and A gives me a subgroup. However, I can also notice that if I just look at B and E, so BE gives me back B, of course, and then BB gives me E, and EB gives me B, right? So I can also have the subgroup of just E and B. And then similarly, C times C is going to give me E, and EC is equal to CE, which is equal to C. So I get EC as a subgroup as well. Now, as soon as I start combining any two of those non-identity elements, so BC gives me A, and boom, I have the whole set, okay? So I can't combine any of the two, but as soon as if I just consider one, I can pair each of them with the identity and we're good to go. So what happens is we get all of Z4, so I'm going to draw some diagrams here. We have all of Z4, and I suppose I'm ignoring here the fact that we can't have just that trivial subgroup of only the identity element. But subgroup of Z4, we can observe 0, 2 as a subgroup of that. But then we can actually observe just the set containing 0 as a subgroup of that subgroup. So it is a subgroup of Z4, this is a subgroup of Z4, but we can observe this as a subgroup of that as well. Similarly, we can take the Klein for group, which we're denoting as V, that was above here, so V, that's what we're talking about, the Klein for group. Now, these are not subsets of one another, so I end up with these 3 separate subsets, which are subgroups, E A, E B, and E C. Now, of each of those, the trivial subgroup is a subgroup of those, right? So this is a subgroup of that, it is a subgroup of that, it is a subgroup of that. And each of these are a subgroup of the Klein for group. So we see this sort of subgroup diagram or this subgroup structure. Excellent. So again, those are our groups of order 4. And we can see that they're not the same. If they were the same, they would have the same collection of subgroups. So this is kind of one of those characteristics that we were talking about for isomorphic isomorphic binary structures. They have to have common characteristics, but they have to be characteristics that aren't just unique to their representation. Well, here I have one subgroup of order 2. Here I have 3 subgroups of order 2. That's very different from one another. So these two things are not isomorphic as binary structures, and we're going to extend that definition to be isomorphism of groups. Now, we haven't said that, we haven't defined it yet. I think that comes a little bit later. I don't remember which section it is. But anyway, so the language should sound familiar since we have the understanding of binary structures. Anyway, we'll continue on in subgroups in just a moment, so I'll see you guys back here in the office.